Hi, welcome for joining us late this morning, early this afternoon on our webinar for innovations in motion and multi-phase flow simulation with STAR-CCM+. We're going to look at what can be done within STAR for modeling mixers and other applications where you might have motion and multi-phase attributes tied along with that. I'm here with George Laird, our principal engineer, and Bjorn Vandervelde.
Hello. I should say hello. Clay is going to be doing the presentation. I'm going to be in the back answering questions. So you're going to see on the webinar, you have an option to raise your hand or put a question, and I'll do my best to answer it. If I can't online, I'll tag it for Clay to answer toward the end. I have about 10 years experience in CFD, but Clay is the lead. So even though I'm the principal, I work for Clay when he does CFD. Bjorn?
Thanks, George. My name is Bjorn. I'm the digital marketing manager here. I work with the team to put on great content that you can use for our customers and for folks who don't know us. Clay, can you go to the next slide, please? So yeah, our software services, we support and sell FEMAP, STAR-CCM+, SimCenter, and as well, we also support NXCAD, NXCAM, TeamCenter, and through George, our CAE director, we also support LS-DYNA. On the right, you can see one of our CAE support reviews from our friend Shri at LTK. He talks about what we've been able to do for him over the years. And looking forward, we in the Seattle area, we will be holding a simulation symposium. It'll be mid to late February 2020, probably February 27th, still nailing that down. And that will be at the Boeing Future of Flight Center. That is right near Everett and Mokoteo, and it's right near Payne Field as well for Boeing. So if you have any CA support needs, or you need training, please reach out to us. You can contact one of these handsome gentlemen here down below at the bottom, and they'll be happy to help you out.
All right. So we'll kind of move into the meat of this webinar. First title slide, we'll be discussing kind of an overview of what we're going to cover. First, we'll give you a little bit of a background review of our CFD experience working with applied CAX and our services side of predictive engineering, and then kind of, a quick review of, why is simulation necessary? Why do we go through this effort? And as I mentioned, we'd like to focus on this webinar applications that are into mixing and wash. Basically, you'll have movement, you'll have multi-phase flow, you've got water splashing around. So we're going to go into kind of an overview of, how do you set up these models in STAR to model motion, to model different multi-phases, either using the Eulerian or Lagrangian method. And we've got two hands-on demonstrations to go through and show. One's a simple paddle mixer where it'll be Eulerian multiphase, just mixing, splashing around some water. And then we've got a ribbon mixer that's going to be just kind of turning some DEM balls. So for over 20 years, we have experience doing engineering services work through predictive engineering. We're not only selling the software, we're active users of the software ourselves. And over this time, we've encountered a wide range of problems. George could probably talk to some of these problems that's shown up here. We've done coupled CFD structural analysis, kind of shown up here in the upper left. Conjugate heat transfer of cooling for test stands of a large jet turbine, and then kind of touching on the multi-phase aspect of what we'll be discussing here is analysis that we've done on silt particle distribution through pipes, and even more recently combustion in a recovery boiler. combustion, we're modeling the fuel that's injected into the lower furnace with Lagrangian multiphase, and that's going through the drying, devolatilization, char burning process, along with all the exterior chemical reaction.
Hey, Clay, can you hear me?
Yep. Yes.
Hey, I want to jump in because I thought this was interesting when you know, you keep saying Lagrangian. Well, even with all my background in mechanics, I have to go, okay, the difference is Eulerian is what is CFD is where the mesh is static and you move your computational entities through the mesh, but the mesh doesn't move.
Yep.
And Lagrangian, well, is what we do in FEA, structural mechanics. The mesh deforms. And and so that's why it's sort of cool when they say Lagrangian particles. What they're saying is they're really shooting things through. They're actually real physical entities that move through the Eulerian mesh. And but you know, I haven't seen that graphic of the recovery boiler. That is impressive.
Oh yeah.
I know.
It's the fuel that's being sprayed in from the sides and going through the combustion process as it goes up to the boiler.
I know. It's like candy art. There's nothing finer than CFD art. Okay, moving on. I just want to jump in that.
All right, and you know, why is simulation necessary? Well, you know, at the basic level, you want to validate that your design works. We have many clients that skip this step and they kind of come back to us with a design that's broken, and then we have to do analysis at that point to figure out why it didn't work and what a possible fix could be. But very smart use of the design would be if simulation is going to be done up front, and using a tool like STAR gives you the ability to, you know, fully explore the design space with optimization packages. And the entire idea and goal is to pretty much shown in this little chart on the right, is you want to reduce the amount of cost, reduce the amount of time to arrive at the optimal solution for your application. You can also do other looking around the design space and come up with innovative solutions, something you may not have originally thought of at the beginning of your design process. The applications for multiphase and motion are quite vast within CFD. Like I said, we're going to kind of focus mostly on the mixing applications now, but you can look at evaporators and condensers, spray painting application with thin film models, aircraft de-icing or aircraft icing is a popular simulation tool, and it's used quite a bit within the automotive industry on vehicle water management. We will get a little bit into discussing of dim particles. That's part of the Lagrangian models that me and George have mentioned. And you see some applications here with additive manufacturing and coating. So to first start off with all this, we're kind of combining, you know, as I mentioned, motion and multiphase. With motion, there's on this slide, you know, three big methods of modeling motion within your simulation study. These aren't the only ones that are available in STAR, but these are definitely the most applicable to the models that we'll be looking at and discussing today. The first type of motion that we're going to discuss is called the moving reference frame. This is basically a time average technique. And then we'll get into discussing a little bit more about rigid body motion. There's lots of similarities to setting up the problem between moving reference frame and rigid body motion, but rigid body motion will give you a time accurate, a transient solution. And then probably the most flexible of all methods for introducing motion into your simulation is going to be the use of an overset mesh. And we have examples that we'll look at using the rigid body and overset mesh in this webinar.
I want to say really the overset mesh is the future. That's where STAR is moving to. And when you build a model and you look at it and you think it makes sense, It usually works 9 out of 10 times, and then it's like the 80-20. You spend on getting that 20% left. You're spending 80% of your life. But the overset, there's a lot of little tricks. But what we're trying on this seminar is to take some of the fear, uncertainty, doubt out of the CFD process, saying, look, these are the generalities. It can be done. How you can set it up. But then there's always that background, the technical support when your model doesn't work. And then that is all you can't do in a seminar. It's just too much information.
Yeah.
You try this, refine the mesh, do this, but that's why it's nice having somebody that's already done the suffering process on the team. Yeah. Back to you, Clay. Onward.
Yep. The first and probably most easiest method setup is a moving reference frame. And this is, as I mentioned, it's a time average technique. It's probably a good thing, at the beginning of the design, if you're only concerned really about a general parameter, such as how much power is this pump or this fan going to take, what kind of airflow might we be able to expect. What you're going to do here in using this technique is you're going to basically define a region that's going to be around your fan blades or your paddle in the mixer that's going to be doing the rotation. You cut that region out of your main region. You have interface boundaries between this, what's going to become a moving reference frame region, and the stationary region, and you apply the moving reference frame to it. And what
wait. But this is just it's a slip mesh. Go to the next slide. I mean,
no, this is the stationary mesh.
So you don't have an interface on it.
You do have an interface. Yep, you do have an interface between this moving reference frame region and the stationary region.
Oh, okay, like the block you're showing up there on top on the right.
Yeah, exactly. It stays stationary. This is actually called a frozen rotor approach.
Right on.
When you apply that moving reference frame, you're basically going to be generating a constant grid flux based on the properties of the rotational rate or the translational rate.
Whatever. So I'll believe you.
Yeah, so you end up generating kind of as I mentioned, a steady state solution to the problem.
Okay.
Now the rigid body motion, this is where you're getting into a slip mesh. This is pretty much set up identically as you would set up the moving reference frame. You're going to cut out a region next to the rotor blades or next to the paddle that's going to be doing the motion. We have in the upper right kind of a meshed example of a ball valve, but you're going to define the area that's moving as a rigid body motion. And when you run this analysis, the cells are physically going to move.
Right, and this is what you did for that ball valve analysis, of course.
Exactly.
The ball valve.
Yep, there's a simple ball valve.
Because this is, on the prior slide, go back to the prior slide. The gig on that is when you know you're going to have a constant rotational velocity, you just give it a spin.
Yep.
And all things are constant and groovy. Now, go to the next slide. The reason why you use a rigid thing is because it doesn't spin like a turbine. You're going to, on the ball valve, it's like, okay, we're going to move it 60 degrees, and flow is going to come in from this side. Then we're going to move it back 30 degrees. So it's the concept is one model, all sorts of different configurations, don't have to do a bunch of rebuilding. And you can also move it dynamically too. Like you can capture shut off.
Yep.
Flow.
That's it.
But you would never use it for the turbine.
Well, that's actually what's shown down here. You see the turbine that was done right here below. This is the moving reference frame solution. It's kind of an averaged flow going through it. And then you see the same plane position done with a moving rigid body motion.
But isn't the computational cost?
Bit more waiver. Yep, that is the downside. Because this is a transient solution, it will be computationally more expensive.
Come on, like 100x?
Oh, I wouldn't say that much. It depends on, yeah. Depending how long you run it out, yes.
100x, that's what I thought. Interesting.
More accuracy, higher accuracy is always more time consuming.
CFD. You never have enough CPUs.
Yeah, and since we're talking about time-consuming and computationally intensive methods, we will roll into the overset mesh motion shown here.
The grand dam. I mean, this is it's like if you see the videos of a bicyclist, you like moving down the road, you know, they're showing the CFD around it. Yeah, that's overset.
Yes, exactly.
Yeah.
Kind of the previous two methods, you know, typically, yeah, you're using it for a rotational element, something where the boundaries between the moving area and the stationary area are pretty well defined. They're not going to move, can be set up for translation too. But the overset mesh, you basically have full freedom of movement. You can also have overlapping bodies. And what we're doing here is we've got essentially a background mesh that we've defined. That's our main continuum. And then around the part that's actually going to be moving, this is actually a water nozzle that's shown here. With the interior walls of the nozzle or the surface of the nozzle, and then just some area around it, we create an overlapping mesh. When we initialize this, that overlapping mesh essentially cuts out a hole in the background mesh and merges the cells between the two.
Well, and it updates it too. I should admit, even though you show 2D, this is all 3D.
Yeah, this is 3D. This is just a cut plane through the middle.
Well, everything you're showing is 3D.
Yes.
Everything. It's just like graphically, it's just easier to describe it and show it as 2D. And the computational, why this is the grand dam and the most expensive computationally, is that what you're saying is that you mesh around your structure of interest. And so you can capture turbulence and everything nice near the boundary, but you're moving that whole mesh body through the other mesh. So like if you update it and move it to one direction, it gets to it transfers everything between the boundaries and the background.
Yeah, you have to share information between the two meshes.
Yes. And sometimes it works. I mean, I've had it work. But But what happens if you bounce up against hard boundaries that are, you know, other Navier-Stokes type boundaries where you have to capture turbulence at it, it can be challenging because it always wants a couple elements between the boundaries. And your mileage will vary. But
we should do a webinar at some point just focused on the overset mesh.
Well, they do. I saw one in Berlin at the International STAR-CCM conference. It was on overset meshing. The whole thing. But anyway.
All right. So moving a little bit into the methods of modeling multiphase, we kind of touched on this a little bit earlier. You've got the Eulerian models and Lagrangian models. As mentioned, the Eulerian models, your traditional finite volume method. You're just concerned about the flow in and out of a cell that's static. And the Lagrangian models, well, we've got the continuum flow in the background. We're injecting particles, and based on the forces on those particles from gravity or from the surrounding flow, lift, drag forces, we can track what the motion of those particles would be through the simulation. On the Eulerian side, we've got, you know, a few different methods available within STAR for doing these simulations, different model setups. First one is a lightweight option called the multiphase mixture method. To a certain extent, this is kind of multiphase. It's kind of not. You're basically taking all your phases and just combining it into one single set of equations. Also, I guess to back up a little bit when I'm talking about phases. With phases, what I mean is, you know, something that's going to be immiscible. So solid, it could be ice that melts into water. You have a water phase, water evaporates into steam. You have a gas phase, or you could have immiscible liquids such as water and oil. So with a multiphase, you're basically taking what you have and just kind of estimating what the properties would be for one single phase. The Eulerian multiphase is actually a true multiphase model where we're tracking each set of phases. Each set of phases has its own set of continuum equations that are being tracked going in and out of the cells. From these, we have extensions such as the volume fluid. This is used when you have a sharp interface between immiscible fluids, such as water and air. We've also got the dispersed multiphase. This is almost kind of a combination of Eulerian multiphase with a Lagrangian multiphase. It's primarily used for very low fractions of droplets or particles, used in icing applications. It could be coupled to a film method. Like Lagrangian multiphase, but we don't really care about what the actual path is. And then lastly, we have a film fluid model. This is interesting, has a lot of use in, say, the automotive industry. We have an example down here of a windshield wipers. You're really just worried about what is the fluid thickness on a surface. So it's just tracking fluid thickness on the surface of a cell or on a cell face. So to get into this and give you a little demonstration of how you can set this stuff up in STAR, we'll look at our first application. It's shown here. This is just a simple vat mixture with a paddle. We're spinning it up to about 240 RPM, and as you can see, as it's spinning up, you have a well that's developing. With this model, we're using Eulerian multiphase between the air and water phases, and we're using a volume of fluid to define the sharp interface between these two phases. So we're going to open up this model, try to go through it real quickly and kind of investigate, one, the geometry, look at the region definition, show how we can apply motion to this, show how we set up the phases, set up the phase interactions, and also get some engineering values out of this, such as evaluating what the shaft power requirements are. So here we are at our model in STAR. We can see the model right here, and if we kind of jump over to the geometry real quick, we actually put this model together using a little add-on in STAR called AddMixDis, kind of shown here. And what this does is it automates geometry building, primarily for mixers. It has a number of different paddle designs. It'll actually run through everything, create the entire geometry. You can create the entire analysis for you.
Clay?
Yep.
Is that a paid add-on?
No, it is a free add-on, although you have to request a license for it because they do want to track
They
usage.
want to track who's using it. No, it's just you know how it goes. I dislike showing stuff where, oh yeah, this really cool thing, but you got to pay extra for it.
Yeah.
Okay, I wanted to confirm. Carry on.
One thing that is nice is it will create the geometry for you shown here, and these are actually parameterized geometries. So we've got like the impeller blade. We could go through, adjust the blade height, the blade length. You could adjust the angle of the blades, the number of the blades, and do a number of, basically just roll this into a design study if you're looking at optimizing.
Right, but I mean, come out of the gate. If we were doing this and we just had one blade and be done with it, come on, it would have taken us what? You make the geometry, you throw it in, 10 minutes.
It wouldn't take that long.
I mean, that's what I thought, because you're showing overset. There's overset mesh, right?
Yeah.
And there's the geometry, so it's not even that. It just gives you the flexibility of having paddle designs right there at your fingertips, right?
Yeah, I mean, so it depends what paddle design you're looking at. For this simple paddle design, it's simple. We could have created it ourselves. But then they've got like, your boat oar designs and some ribbon mixers and things that get, well, that would be a little bit more complicated.
Right on. No, okay. Sorry for the interruption. Back.
Yeah, so you see we got like our two regions here. We've got our static region, which is pretty much the tank walls. And then we've got the impeller region, which is right next to our paddle that's going in. And that's defined over here. Now, first thing we'd like to do is we need to apply this motion to the impeller region. What we suggest doing is kind of going down to tools, and we have a couple field functions set up. One's just our basic RPM field function, the scalar value. This can be changed at any time. But we go over and transfer that to a kind of a field function to do two things. One, transfer it to radians per second, STAR can do this itself, but what I really wanted to do was basically add a ramp onto it. So within the first second, it goes from 0 to full speed. And then after the first second, we're holding it at full speed. And this is kind of the Boolean statement for doing this type of function in here, where we have our Boolean statement right here. If time is less than 1, you've got the value if true, a semicolon, the value if false. So now that we have our field function for velocity defined, a time-dependent velocity that's defined, we can go over to the motions and create a new rotational motion. We want the axis to be in the Z direction. And when we go to our rotational rate, it's easy just to go over and call back to that field function. And we've got that set right there. Now, if we go back up to our region, we go to our motion specification and now just grab that rotation that we defined. And we've got rotation now defined on this rigid body part. We can see we have an interface between this. Now, one thing to notice is, well, we've got the static region, we've got the shaft going up through the center. So that shaft is actually going to be turning too, but it's a static region. If you want to have a little bit more realism on this, we can also just go locally to the shaft on our tangential velocity specification. Now change that to a rotation rate. And our relative rotation, then we apply our field function and go back and call that field function again for omega. So now that we've got our rigid body motion set up in our model, we can now go over to the continua and apply our physics. And we've got most of our physics already set up, except the area defining the multiphase and defining the interaction. So for this model, we just want to grab 2 phases. We're going to be simple and grab it as air and water. Get our constant density for the water, and we can rename this water. And again, for the air, and it's simple, just gas constant density for now. So if we kind of look over at the water real quick, the default values for anything that's going to be liquid, it's going to be water. Anything air, it's going to be, or anything that's gas, is going to be air within STAR-CCM+. Kind of open up our material properties for dynamic viscosity. We can kind of see you've got a constant dynamic viscosity for Newtonian fluids. If you didn't want that, if you had something a little bit more exotic, you got a couple non-Newtonian models set here, or you can define a field function for something that's custom. So it doesn't have to be a simple Newtonian fluid for your liquid phase. For the phase interactions, it's also going to be quite simple, defining the volume of fluid phase interaction, which we kind of already have down here. For volume fluid, we still need to define what the primary phase, air, and the secondary phase is going to be. Now we're almost ready to run, but the first thing you also have to do is define what your initial conditions are. We have the water is going to be filled up to some point here, so it wants to know what the volume fraction is going to be. And we have it set up for composites, asking for the water. And again, we go down to the tools in our field functions, and we've got one that's already defined, liquid fraction, where basically we're saying anything in the z-axis under this height value, about 25 millimeters, is going to be 100% water. Everything above that's going to be air. So again, we just go through and apply this field function. Now, to make sure that we have that done correctly, we'd like to see what the surface is going to be. And you'd like to see what the surface is going to be during your simulation. You can create a quick ISO surface based on the volume fraction of the water.
I want to tell the team that's watching that what Clay's doing, he's doing a real analysis. If you want to just make a demo, you know, like here, I can make a mixing analysis in 5 keystrokes. He could have set it up with some macros and other stuff, but what we try to do is we want to make these seminars as user guides. Something like, no, this is real. This is what you really have to do to make a simulation, and not smoke and mirrors. That, yeah, you do have to go through, and it can look daunting at first, you know, with these picks, but once you're sort of like past the FUD, the fear, uncertainty, doubt on the interface, it really makes sense. It really has a flow to it.
Yeah.
It's, you know, it's like, yeah, it's very logical. It's just, so this is why he's doing these picks. This is real.
Yeah.
Back to you.
Yeah, as you can see here, we've gone through this little green button up here. This will just initialize your solution, take your basic input initial conditions, apply it to your mesh, and we can see we now have a flat water level. It's about 25 millimeters of where we stated before. And just to show you real quick, if you want to apply, you know, make a couple quick reports to put out what the shaft torque would be, this is kind of already set up in STAR. Go into new report, and it's going to be a moment. And what you want to do is just go back to that impeller region, not the whole impeller region, but you can grab the main surfaces that will be on the paddle blade itself, and you have a moment function that you could rename as torque. And with one click, we can go to create, monitor, and plot, and we have a plot that we can look at what the output torque would be. Kind of doing the cooking show method. This analysis, we did run it. We ran it for about 12 seconds that you saw in the animation. And I think that took 6 hours on 32 cores or something like that to run. At the end of the run, we get kind of our velocity plots. This is what you'd see at the end of the 12 seconds demonstration, where we've got our well that's been developed. And if we looked at our shaft output torque, we've got the torque plot here. And we can see during that 1 second ramp up I did, there's high torque as everything's accelerating, and then the torque kind of steadily comes down, and it's drifting off a little bit as we're developing that well. So we'll move on. We'll move on to our next application, to the multiphase models. Discuss a little bit about the Lagrangian methods. And there's 2 main Lagrangian methods within STAR. You've got the Lagrangian models, LMP, and you've got DEM, discrete element method. The Lagrangian multiphase, you're essentially injecting a number of particles into your simulation flow. Usually you're doing this with sprays, droplets. So you have thousands, millions of little particles you're injecting, and it'll group them into what they call parcels, and track that parcel throughout the flow. This has many uses. It can be done for steady state. It can be done for transient analysis. The particles can be part of reacting flow if you're doing combustion, either a liquid fuel or a solid fuel. But with this, the LMP models will calculate the particle paths, and that path will be saved, and you can go back and plot what the particle path was for a transient or a steady state analysis, and, you know, look at different components about, you know, velocities or temperatures or mass fractions of that specific particle. The DEM method is a little bit more of a robust version of LMP. With LMP, when you define the phase, you're just kind of setting up, you know, maybe that phase interaction with different surfaces. With DEM particles, the big thing is you not only have the phase interaction with different surfaces, you also have got body-to-body interaction. Every particle is essentially almost an independent particle that you're tracking. It can bounce against the walls, it can bounce against itself. You've got other models available in STAR where you can clump these particles together. If you're starting off with a baseball solution, build up a custom particle shape. There's some other particle shapes available, such as cylinders and tubes in STAR, or you can even do a polygon particle. but they can clump together, they can tear, break, you can add adhesion to it, so these particles kind of join together as they're mixing around in a certain mixer. We have quick little demonstration here of DEM particles in a dryer, and you can see kind of the moisture content as these things are getting dried off and water is evaporating off of them. So kind of at the beginning when we started, me and Bjorn were first talking about putting together this webinar and kind of focusing on mixing. We had a few other clients that we were talking to at the time that had some interest in mixing analysis. There was the idea of ribbon mixers came up, and I haven't really dealt too much with ribbon mixers. So what I did was start searching online YouTube videos and found a couple examples of ribbon mixers. And I found this one video kind of shown down here. We haven't ever worked with this company. I just found this video on YouTube. But when I looked at this video of demonstrating their machine, that just looked exactly like a DEM analysis to me. They've got a bunch of discrete foam balls that are kind of turning around within their vat. So I basically decided to try to put together an example myself, shown here, where we've got, say, blue, red balls. These are rubber balls that are just turning around and being mixed in a ribbon mixer. This is actually using an overset mesh to model the motion of the blades. It could have been done with rigid body motion, but we thought this would be a good application just to demonstrate the use of a overset mesh. One advantage of an overset mesh too is if you wanted to make a modification, let's say two ribbons that are standing next to each other in a wider vat that might be intermixing with the space, that would require the overset mesh. So we're going to open up this model real quick and kind of go through just how is that set up, how's the over mesh defined, and poke around a little bit of how we set up the DEM model itself. So if we jump in, again, we've got our geometry right here. We can look at the CAD model. The CAD model for this was fully created within the STAR-CAD system. You can see you've got basin, overset, mesh elements up here. We've defined that into two separate regions, the main basin, which just has one surface. It's just the walls of this kind of half circle trough type shape. And then we've got our overset region here. If you look at the overset region, it looks like a very thick version of our ribbon mixer itself. But you've got the outer walls of the overset region, and then you've got the actual physical ribbon walls themselves. If I move over to the section mesh here, we can see where we have the overlap between the overset region and the background basin mesh. And some things to kind of keep in mind if you are employing an overset mesh is, one, you like to kind of make sure that the mesh size between your overset region with respect to your background region is about the same size overall. And you'd also want to make sure that you've got at least 4 to 5 cells that are overlapping between the overset and the background mesh region. If you don't have that, you may run into issues and cutting out the hole in the background mesh that would lead to simulation instability or just not running of the simulation properly. If we move over to the continua real quick, we've got a DEM particle continua right up here. Our Lagrangian multiphases are defined here, and these are already going to be predefined for this demonstration. We've got DEM1 and DEM2, and both of these are essentially just, if I look at the properties, rubber balls, everything with the default options set. Interesting aspects when we look at the multiphase interactions. If we look at the multiphase interactions, we see we got to create interactions for DEM1 to DEM2, the two phases, each phase with respect to the walls. and each phase with respect to itself. In all these phases, they can be customized. Like I said, you could add additional models such as artificial viscosity or cohesion, so these could stick together. Basically, model something that might be a little bit more of a viscous granular flow. So we've got that set up, and if we go to our view scene, right here, we can see this is what we were showing in the video. We've got two injectors set up for DEM 1 and DEM 2, and both of these are using field variables to calculate how the flow is dumped in, because we've got this set up right now so that in the first 1 second we dump in phase 1, and then in the first second we dump in phase 2 through these field functions. And again, as you see here, it's using the same little Boolean statements that we were showing before. Now, one thing, when you get all this model set up, it's always good to do with a overset mesh is to confirm that you actually have your motion set up correctly. And an easy way to do that, here's create a new continuum that's called motion test. If we look at the models in this motion test, we don't have anything. All we're defining, it's three-dimensional, it's implicit unsteady. There's nothing with respect to flow or dim particles in it. We can switch both of these guys over to that new physics continuum for the motion test. And the overset, as I mentioned before, you're applying your motion to this as a rigid body motion, same way that was shown before. We have a motion set up here. We want to create a test rotation. So we don't wait for the rotation to start. We're just going to hit run and go back to the scene. And hopefully what we should see is this paddle starting to click along as the motion has been correctly applied to it. All right. So that's kind of wrapping up a lot of what we have to show in this webinar. Got some help here for further information on reading. Again, we always suggest, go to the documentation within STAR-CCM+. You can access this either through help or hitting F1. Documentation within STAR is actually very, very well presented on, workload, work-throughs, as well as the theory behind it, plus many tutorials that are presented. There's also, if you have access to the Steve portal, quite a lot of interesting articles on the Steve portal that you can get. The first one here in this link is a reference of, whether or not you should use moving reference frames or rigid body motions for your simulation. As we discussed before, are you just looking for a steady state solution, or you want to get accurate transient results?
Yeah. Hey, Clay.
Yes.
What I'll jump in and say is that the way that we've learned through this, because there's always something new and to figure it out. So we'll go through the online manuals, and then we'll look for simple examples. And you never have enough examples, so you look and try to do something out of the online. The Steve portal has it's quite a treasure trove of stuff.
Yeah.
And it has lots more of examples, but it can be pretty overwhelming at times trying to find out what you want. That's one of the things about STAR, why it works off a subscription, is that everybody always has a high level of tech support. So
yeah,
the gig is usually you give us a call, or a client, or if you're looking, and we'll outline, okay, this is the way we approach it, this is the way you're going to learn it. We'll recommend some examples to get you started, so you can get off of ground not zero and start making progress. But yeah, the first model is always a bit painful.
Yeah, the first model is always painful. one interesting article I'd point out here is this one. It's very similar to the vat mixer we did, except they're using an adaptive mesh to better refine that interface between the air and the water. But yeah, there's a wealth of information available on the Steve portal. And I believe that kind of wraps up what we have today. I'd like to thank you for your time.
Go have lunch.
Thanks, everybody. We'll be following up with a recording of this presentation.
Thank you.
Thank you. Have a good
All right.
afternoon. Bye-bye.